Good evening, guys. Hope you're doing well. I'm going to walk through colligative properties with you guys now. I've been having some problems with this screen sharing on my Remarkable, so I'm going to write my notes out and then I will upload them so that you guys can see my hand scratching, but I'm not going to be able to do that while we're sharing. I can show you my calculator, but that's about it. All right, I'm going to go ahead and share with you, so hopefully we can get this taken care of, and hopefully we won't have to do this in 8 million pieces. So, colligative properties, that's what we're talking about tonight. Colligative properties is actually one of my favorite topics. So, that'll be fun. At least I think it'll be fun. Properties of liquids, we'll talk about types of solutions, effective temperature on solubility, effective pressure on solubility, our colligative properties, which, as you can see here, vapor pressure, lowering, fractional distillation, osmotic pressure, boiling point, elevation, freezing point depression, and using colligative properties to determine molar mass. And then we'll talk about how electrolyte solutions are slightly different than what we've talked about in the past. Okay? So, let's talk about the following transitions. We've talked about them before, but it was a bit ago. So when we go from solid to liquid, we are melting. Okay. Gas to solid is condensation. Or, yeah. So solid to liquid is melting. Gas to solid is deposition. Gas to liquid, on the other hand, is condensation. Liquid to solid is freezing. Solid to gas is sublimation, and liquid to gas is vaporization. So those are the things you need to know about. Those are the 6 terms that you will need to be responsible for. And we talked the last time about what compound this was for. And of course, how do I know what it is? Well, it's for water. And I know it's for water because the slope is negative. So that's how I know that that's a water diagram. All right. So let's go ahead and see if we have any questions, comments, problems. If you do, you know what to do. Let me know. Send me an email. Drop by my office. Give me a call, and we'll see what we can do with that. Okay. Let's see what we're talking about here. So when we talk about the properties of liquids, we can talk about the surface tension. So molecules and liquids are pulled in all directions by their intermolecular forces. But at the surface, they're always pulled down and sideways. There's no up. And so we get this tension that exists at the surface because of that. So surface tension is the amount of energy required to stretch or increase the surface of a liquid by a unit area. And you can see in, like, if you put a burette, you can see when you put liquid in a burette, it goes up the sides a little bit, and that's how you get the formation of the meniscus. That's called capillary action. That the action of cohesion and adhesion pulls the liquid up in the gas tubes, and that's because glass tubes are actually negatively charged, and so there's an interaction between water and those tubes. So water has a higher than expected surface tension because of all the hydrogen bonding that takes place in the water. So we wouldn't have expected it to be like that. But now that we know about hydrogen bonding, we can predict it. Okay. Viscosity is a measure of a liquid's fluid's resistance to flow. It's usually a lower value as temperature increases. Okay, so as things get warmer, they move better, they move faster, so it's less viscous. Strong intermolecular forces mean higher viscosity. So because water has so much hydrogen bonding, again, it has a much higher viscosity than something that does not. Okay. So water, we've talked about it a couple of times. It's weird. It is totally weird. It has a lot of strange properties, and that's because it can form 2 hydrogen bonds per molecule. So it gives us that high surface tension, the high viscosity, high specific heat, and the density of water is higher than ice. So those are all differences from what we would expect because of that hydrogen bonding. Okay. We can talk about types of solutions. So I can have a gas dissolved in a liquid. You've probably seen this. Excuse me. If you ever had a carbonated beverage, you have a gas dissolved in liquid. So soda has CO2 in the water, and that's something that we can talk about there. We have solids and liquids. So it's a liquid solution. We dissolve a solid in it, dissolving salt, table salt, in water. like to cook pasta. I know I do that. That's one of these solid liquid interactions. You could also have a liquid liquid solution where we have one big component and one small component, or roughly equal type measurements. Whatever's in bigger component, we say that that's our solvent, and our smaller component is the solute. So we can dissolve ethanol in water. It doesn't mix particularly well, and you've probably seen this. Oil and water is a mixture like this. So that's a liquid-liquid mixture. It's not a great one because there's phase separation that tends to happen. And that's because the densities of those materials are different. So liquid-liquid solutions, unless they have very similar densities, do not actually make a homogeneous solution. They will eventually phase separate. A couple of terms that we use when we talk about solutions. Saturated. That means that it contains the maximum amount of the solute that will dissolve in a solvent at a specific temperature. So that is temperature dependent. We have unsaturated. So we can have more stuff go into solution. And again, that is temperature dependent. We also have something called supersaturated, which means that I have taken something like water. I've put some glucose in it. I heat it up. A lot of glucose will go into solution as I heat it. And then it comes back down in temperature, but I don't disturb it. And if that is the case, and I've come down in temperature, and I were to suddenly disturb that, like poke a stick into it, then all of that sudden comes crashing out of solution. And that's because it doesn't belong there at that temperature. So that's what we see with supersaturated solution. That's actually how we make rock candy, is by supersaturating that solution with glucose. And that's how we get that, okay? We have several different ways that we talk about concentration. The most common is molarity. Molarity is defined as moles of solute per liter of solution and is given a big M, capital M. It's easy to measure. It's used for to discuss solutions for titration and gravimetric analysis. It's the one we use a lot. We also talk about percent by mass, which is the mass of solute over the mass of the solution. So both are masses percent by mass, and it's percent, so it's 100. So percent by mass. This is used for things where molar mass is unknown, therefore, and it's independent of temperature. So it doesn't matter what the mass is. I can't convert it to moles because I don't know what the mass is, but I can look at its mass percent. We can look at something called a mole fraction. Excuse me. So sorry, so tired. A mole fraction for a component. We calculate the number of moles of that component, and we divide it by the sum of all moles that are present. So total number of moles on the bottom, moles of that particular component on the top, and that's a mole fraction. It's symbolized by chi, and chi A is the mole fraction for A. We use that to look at partial pressures of gases and for vapor pressure. Okay, in both cases, we need to know how much of it is from this particular material, and therefore we can use that mole fraction to multiply times the total pressure to get a partial pressure, or to go from partial pressure to total pressure to know how much of that is from that particular material. Okay, we talked about molarity. Now let's talk about this thing called molality. Molality is moles of solute per kilogram of solvent, and it's symbolized by small m, all of these m's everywhere. The deal with molality, we don't use it very often, but it is moles of solute per kilogram of solvent. And the reason for that is that it's temperature independent. So we can use it for things where the temperature is changing. So things like freezing point depression, boiling point elevation, where we're talking about changes in temperature, we need to be able to look at something that's independent of that temperature. So that's what molality is for. You will need to know not only what all of these things are, i.e., is this a molality, is this a molarity? You'll need to know what the symbols are, i.e., little m for molality, big M for molarity, chi A is a mole fraction. But you'll also need to be able to interconvert these things. The practice will give you a chance to look at the interconversion of those factors. So you should be able to do that, okay? So those are our concentration units. Okay, Awesome. Well, when we talk about the effect of temperature on solubility, generally speaking, for most solids, solubility increases with increasing temperature. There are a couple of things that don't. If you've ever made gravy and you've made it by using cornstarch, you know that you need to dissolve the cornstarch in very cold water. And then as you heat that water by adding it to the rest of it and heating it up, it thickens. And that's because it's less soluble at that higher temperature. So that's where we look at the change in solubility based on temperature. And that's inverse from what we typically see. So a lot of things, sodium chloride, glucose, as we raise the temperature for those, we'll get more that go into solution. And we know there's little to no correlation between the heat of solubility, this delta H solution, and the change in solubility with change in temperature. Okay. Now you may not understand what delta H solubility is, and that's okay, but there's little correlation between the two. Fractional crystallization is possible since solubility changes very differently based on temperature for different materials. So we can see a big change in one of those versus another one, depending on what temperatures we're looking at, what conditions we have. And so that's how we can do fractional crystallization. Okay. Gases. Solubility of gases decreases with increasing temperature. Ever left a soda in a hot car? What happens to it? Gets hot enough, it explodes. Why does it do that? Because the gas has decompressed. It's come out of that solution, made this huge thing of gas, and there's no space for all of it. There's too much pressure, so it just blows up. That's how that works, okay? So the more energy a gas has, the easier it is for it to escape the liquid phase. Since higher temperature means higher energy, then at higher temperature, we have less stuff in the gas phase. So as the soda gets warm, it loses its carbonation, and that's because the carbonation, the CO2 has the ability to move out of that solution because it has higher energy, okay? So that's temperature and solubility. Now we're going to talk about something called Henry's Law. Henry's Law says the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. Right. So the amount of gas that will dissolve in a solvent depends on how frequently gas molecules collide. So higher atmospheric pressure leads to more gas molecules being dissolved in a solution. One of the ways that you can think about this is when you open a brand new soda, you hear it crack, right? Oh, sorry. And right after you crack it, there's an escaping of gas. And that's because we've overpressurized that container so that we can keep as much of the gas in the solution as possible. That's how that works. So it stays higher, more soluble because of the higher pressure. Okay? So that's what Henry's Law is about. And yes, most of my examples do have to do with soda because I'm obsessed with it. Questions, comments, problems on any of that? Hopefully not. Those are all definitions. Those are concepts that you should be familiar with. You should be able to put those definitions down on paper if you're asked to do so, or you should be able to look at something and say, this is the effect caused by, that kind of thing. And the practice will give you practice with that. Colligative properties of non-electrolytes. So, colligative properties are defined as properties that depend only on the number of soluble particles in solution. It does not matter what those particles are. It really does not matter at all. Okay. Now we'll see one case where it does matter, but that's later. So except when they ionize. So if we're talking about sodium chloride, that's a different effect than we have with glucose, because glucose will dissolve, but it doesn't come apart. Sodium chloride, when it dissolves, it becomes Na plus and Cl minus. So that's different. Okay. When we do this, when we talk about colligative properties, we need to look at molality concentrations. So remember, when we talk about molality, it's moles of solute per kilogram of solvent, because that is an temperature-independent measure. We're looking at how these things change with temperature. Okay? So one of the things that we talk about is the vapor pressure lowering. Solutes that do not have an appreciable vapor pressure on their own still lower the vapor pressure of a solution compared to a pure substance. So what we're talking about is the pure substance would be the P01 that we see over here. This P01, where that's our initial vapor pressure. If I put something in that, what's going to happen is that at the surface, I have less of those molecules that I was initially looking at. So rather than being all water, I may see a sodium, I may see a chlorine. And all of those mean that we have less ability to escape that liquid because there are other things present. So the vapor pressure is going to lower because of that. All right. And that's going to be dependent on how much of that material I have in solution. So that's why we look at that mole fraction, because we need to know how much of it is the solute that I added comparative to the number of particles that I had to begin with. Okay. So it's a mole fraction. So the solution with solute is less ordered than the pure solvent, and so that's more favorable. So it's more favorable, so it's less likely to vaporize. All right. So it's happier with the stuff in it, so it doesn't need to vaporize. Okay. A couple of other things that we talk about. Fractional distillation. We talked about this a couple of minutes ago. Separation of liquid components based on their different boiling points. Okay. If two materials have different boiling points, I can boil them and collect the vapor to condense it. So if I have two different boiling points, the one with the lower boiling point is the one that's going to boil first, and that means that it's going to boil and I can collect that gas. When I do so, the gas that I collect is going to be almost entirely the material with the lower boiling point. And so over time, we can keep doing this to get a higher purity of that material. Okay. The vapor is higher in concentration with the material that with the higher vapor pressure. And we can repeat that process many times to increase the purity. Okay. One other thing we talk about is osmotic pressure. So osmosis is the selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. Okay. So if I have a membrane and I have two solutions on the different sides of it. So if my membrane is here in the middle of me and I have two solutions, one here and one here, right? The one that's the more concentrated is going to get more solvent going towards it. We're trying to equalize those concentrations. So the pressure difference that results from the solvent going this way is what we're measuring with osmotic pressure. So as the solvent moves over, pressure on this side of the membrane is higher than it is on this side. So that's what we're looking at. And we can calculate that by using this equation right here, where pi is the osmotic pressure, this is capital pi, is the osmotic pressure, m is the molarity, r is the gas constant, and T is the absolute temperature. Now, since we're doing this at a single temperature, I can do molarity as opposed to molality, okay? So that's osmotic pressure. So we talked about vapor pressure, fractional distillation, and osmotic pressure. There's a couple more that we need to talk about. And that's freezing point depression and boiling point elevation. So here in the South, we don't necessarily talk about this very much, but if you've ever been somewhere where it snows, they tend to put salt, sodium chloride, down on top of the snow. Why do they do that? Well, because if I add that material to that snow, then it's going to lower the freezing point, which means that we then don't have ice, we have liquid water, okay, which is less of a trip hazard. We also see boiling point elevation. That's one of the other things that we talk about. So I was talking a couple of minutes ago about putting sodium chloride in my water when I make pasta. The reason that I do that is because the temperature goes up when I do that. And because the temperature has gone up, that means I can cook my pasta faster. And I like the way it happens when I do that. Again, since we're talking about changes in that temperature, we have to look at using the molality, right? We look at the change in temperature. So delta TF is the change in temperature for freezing. That's why it's F. So change is delta T for temperature, F for freezing. And that's equal to the molality times this factor called KF. So KF is the molal freezing point depression constant. It has units of degrees C per molal. Those values have to be provided to you, or you look them up in a table. There is no way, well, I mean, you can solve for them if you're given the right information, but that's information that you need to be able either be told or asked to solve for, okay? Same is going to be true for our boiling point elevation, except that now we're going to be having our temperature go up. So we have a slightly different expression, although virtually the same. That change in temperature for boiling is equal to our boiling point, a molal boiling point elevation constant, again in degrees C per molal, times the molality. Okay, and again, that value, same as we talked about before, has to be given to you, has to be looked up in a table, or you're solving for it based on the change in temperature and the molality of that solution. Okay, now you may have to calculate the molality before you can do that, but that's one of the things that we can do. Okay. Questions that we might see related to this. Let's take a look at those. So when we look at freezing point depression, we consider the dissolution of glucose in water. The water is 150 grams. There are 12.6 grams of glucose, which has a molecular weight of 180.156. What is the change in temperature for the freezing point and boiling point of this solution? Now they give me Kf, which is for the freezing point, as 1.86 degrees C per molal, and Kb, which is the boiling point elevation constant, as 0.52 degrees C per molal. Okay. So the first thing I need to look at is what is the molality of this particular solution? So molality, that little m, is defined as moles of my solute per kilograms of solvent. Okay. So I'm going to have to calculate moles of the solute, and I'm going to have kilograms of salt. So moles of solute, I need to take the 12.6 grams of glucose. I divide that by the molecular weight, 180.156 grams per mole. Okay. And then I get 0.0699 moles divided by the 0.15 kilograms. Okay. So 150 grams is 0.15 kilograms. When I do that division, I get 0.466. And like I said, I will send you the notes for how I get all of this, what it looks like on paper when I do it. That information is then going to go in here. So our change in temperature is going to be the 1.86 degrees C per molal for the Kf times the molality that I just calculated, the 0.466 molal. And that tells me that my delta Tf is equal to 0.867 degrees C. Now, that is the change in temperature. That's delta T. If I want to know what the final temperature is for freezing, I need to take this delta T and subtract that from the initial temperature. So for water, initially we freeze at 0 degrees C. We subtract the 0.867 degrees C, and that gives me a final temperature for freezing at 0.867 degrees C. Okay. We can go through a similar calculation for the boiling point elevation. Now, the molality is exactly what we calculated before. There's no change in that situation. But we have a slightly different calculation because Kb is not the same as Kf. So when we plug in the Kb, the 0.52 degrees C per molal, times the 0.466 molal, that gives me 0.242 degrees C. So that's my change, the 0.242 degrees C. If I want my actual boiling point, I take my initial boiling point, 100 degrees C, I add the 0.242 degrees C, and that gives me 100.242 degrees C. So again, the process here, calculate the molality, get or be given that constant, Kb or Kf, calculate the change in the temperature, then add or subtract that from the standard boiling point or freezing point. And it's add if it's boiling point, subtract if it's freezing point. Okay, so that's the process that we're looking at there. All right, bear with me just a moment. Awesome possum. So that takes us through those two. Let's talk about molar mass determination. So one of the things that we can do if we rearrange this equation, we can see that the molality is equal to the change in the freezing point temperature divided by the Kf, so that molal freezing point constant. From the molality, we can calculate the number of moles if we know the mass of the solution. From there, if we recover and measure the mass of the solid, we can find the molar mass. Right, that all sounds like gibberish to me. So let's see what we're talking about here. I have a 7.85 gram sample of a material that's C5H4 empirical formula. It's dissolved in 301 grams of benzene. Kf for benzene equals 5.12 degrees C per molal. Freezing point of the solution is 1.05 degrees C lower than it was before, or the molar mass and the molecular formula. So the molality is equal to the delta TF over the KF. The delta TF is 1.05 degrees C, because that's what they told me. It's 1.05 degrees C below that of pure benzene. And the KF that they gave me is 5.12 degrees C per molal. So if I divide the 1.05 degrees C by the 5.12 degrees C per molal, that gives me 0.205 molal. Okay. I know that I had 301 grams of benzene, right? And I know that the molality is 0.205 mole per kilogram. So if I multiply by the number of kilograms, the 0.301 kilograms, then that's going to leave me with the number of moles, okay? And if I have that, that gives me 0.0617 moles of whatever this material is. I know that I have 7.85 grams of this material. I know that that mass is 0.00617 moles. And so that means that it's approximately 127 grams per mole. I know that this molecular formula, or the empirical formula, the C5H4, is 64 grams per mole, right? Because I have 12.01 times 5 plus 4 times 1.01, and that gives me 64. If I'm not mistaken, I'm just going to double check because I'm being paranoid. 64, yep. And if that's 64, and I'm looking at an overall mass of 127, I divide that overall mass by the 64 grams per mole that are from the C5H4, that gives me a ratio of approximately 2. So I know that I have to take 2 times C5H4 to get my molecular formula, which is C10H8, okay? So that's how we do that. Now remember, we did some calculations early on in the term where we looked at how do we get from empirical formula to molecular formula? How do we, how do we make that work? Well, this is the way that we get that in a lot of that information, okay, about how, what is the actual molecular mass of this thing. This is one of the ways that we can determine, okay? So questions, comments, problems about that? I hope not. That is molecular mass. One more thing that we want to talk about. So one of the things that you may know if you're not from here is that we often use salt to modify the freezing point temperature of the solids, the ice on the ground, right? Well, why that? Is it just because it's cheap? Is it because it's available? Well, Yes and no. Remember I talked about the fact that it was an electrolyte? And so when it goes into solution, it comes apart completely. So NaCl becomes Na plus Cl minus. And remember, I said that colligative properties are not dependent on what material I use, just how many particles there are. So if I have one thing that goes into solution and becomes two, that's more effective than just one thing, right? Same is going to be true when we look at any other salt. So we need to know how much it comes apart to be. That coming apart to be, that how many particles do we get out of it, is something we call a Van't Hoff factor. So it's the number of particles a material makes when dissolved in solution. So glucose, while it dissolves, it does not dissociate. So its I equals 1, right? NaCl dissociates, however. So rather than being 1, it's going to be 2 because I get an Na plus and a Cl minus. If I were to talk about Mg3PO42, I get 3 Mg2 plus and 2 PO43 minus. 2 PO43 minus. 3 plus 2 is 5. So I equals 5 in that case. And then we need to add that to the equations that we've been looking at for three things: the delta TF, the delta TB, and the osmotic pressure. So freezing point depression, boiling point elevation, and our osmotic pressure all need to incorporate that I. Okay. So I don't like to remember more than one equation. So what you'll see on the test is actually those equations right there with the I in it. And understand that we can leave it out if I equals 1, so it can be omitted. That's what we're talking about there. All right. So let's talk about how this changes what we calculated before. So we had this scenario before that we talked about. Freezing point depression, boiling point elevation. We have new equations, I, KFM, I, KBM. All right. You may see this if you're out on the internet as negative I, KFM, and that's to remind you that it's depression. Let's talk about this again, okay? Consider dissolution of magnesium phosphate in water. Water is 150 grams, 12.6 grams of magnesium phosphate. Molecular weight is 262.855 grams per mole. What's the change in temperature for the freezing point and boiling point of this solution? Okay, fine. So let's talk about this. First thing I want to do is calculate the molality. Okay, so molality is defined as moles of our solute per kilogram of solvent. So if I want moles, I need to take the mass that I have. I have 12.6 grams of Mg3PO42. I'm going to divide them by the molecular weight of 262.855 grams per mole. And that's going to give me, I know it's there, 0.0479 moles of that material. I then divide that by the 0.15 kilograms. And it gives me 3.319 molal solution. Awesome. I know that if I want to calculate delta TF, that's equal to I KF M. My I for this is 5, because again, we get 3 of the Mgs plus 2 of the phosphates, so that gives me an I of 5. My KF is 1.86 degrees C per mole, because they gave it to me. I also remember it, but that's because they gave it to me. And then I multiply that by the 0.319 mole that we just calculated. And that gives me 2.97 degrees C. And so my T, and that's delta TF, TF is going to be 0 degrees C minus 2.97 equal to negative 2.97 degrees C. If we were to look at the boiling point elevation, we'd be looking at a similar situation, we have the delta TB equals the IKBM, which is equal to 5 times the 0.52 degrees C per mol, which is for the KB, times that 0.319 mol, and that's equal to 0.831 degrees C. Since I want to look for TB, I take my original temperature, 100 degrees C, I add the 0.831 degrees C, and it gives me 100.831 degrees C as my final TB. So process again is the same as it was. Calculate the molality. Then we know how many particles the material becomes in solution. We get or are given the constant, we calculate the change, and then we add or subtract that from the standard boiling point of freezing. Okay? Awesome possum. So the practice that you guys have should take you through almost all of this. Like I said, I will put up the notes about how this stuff is calculated so you guys know what's going on with that. All right. Hopefully you guys are okay. If you're not, you know the drill. Contact me, email, phone, whatever. Let me know that you have questions and I will be happy to answer them. Thanks, guys. I appreciate it. I will talk to you soon.